Imagine you run a growing pizza business. You have exactly 1,000 scattered customers across a massive, unorganized city grid, and you've just secured the budget to build 3 new delivery kitchens. Your primary objective is simple. You want to figure out the exact physical locations to place these 3 kitchens so that the drive time to every single customer is as short as possible. Trying to guess the best spots by staring at a map would take forever. Luckily, there is a mathematical tool designed specifically to solve this exact problem automatically, the k-means clustering algorithm. The name sounds intimidating, but it breaks down easily. The k simply represents the exact number of groups, or in our case, the number of kitchens you want to build. Here, k equals 3. The means refers to finding the average mathematical center point, also known as a centroid, of those groups. By mathematically locating these exact center points, you can take a completely unorganized map of data points and efficiently divide it up into highly optimized service areas. Here is how the algorithm actually works. First, it drops your 3 kitchens in random spots. Then, it calculates the distance from every single customer's house and assigns them to their nearest random kitchen. In step 2, the kitchen moves its location to the newly calculated geographic center, the centroid, of that specific group of assigned customers. The algorithm operates in an iterative cycle. It constantly repeats this process, checking the distances, assigning the houses, and moving the center point, over and over until the kitchens lock into place and stop moving entirely. This brings us to a technical term called inertia. In our pizza scenario, inertia represents the combined total driving distance for all deliveries. The algorithm's primary mathematical goal is to minimize this inertia. By driving that total distance down, it creates the tightest, most efficient clusters possible. This makes k-means an unsupervised learning algorithm. It requires no human instructions on how to group the items. It creates order out of chaos purely by minimizing the physical distance between points and their centers. But this raises a complication. What happens if you don't actually know how many kitchens you should build in the first place? What if you don't know the correct value for k? To figure that out, data scientists use a standard technique called the elbow method to test multiple different cluster numbers and find the optimal fit. This chart plots total inertia on the y-axis against the number of clusters on the x-axis. You read this graph by looking for the elbow point, the exact spot where the steep decrease suddenly slows down and levels out. Selecting this specific point on the graph gives you the perfect balance. You get tight, highly efficient clusters, but you avoid unnecessarily overcomplicating your model with too many redundant groups. Now we can transition from mapping city streets to analyzing abstract data. To do this, we'll use a classic machine learning dataset containing measurements of iris flowers. Our new technical objective is to take a completely unlabeled list of flower measurements, specifically the sepal and petal lengths, and use Python to group them into 3 distinct flower species. The Scikit-Learn library executes this process with a couple of lines of code. We tell the model to create 3 clusters and fit our data. The immediate output is an array of numeric labels, proving the model successfully categorized the raw numbers into distinct groups. This scatter plot shows what that mathematical grouping looks like visually. The individual data points naturally separate into 3 distinct color-coded clusters, with each cluster representing a different species of flower. The algorithm identifies these hidden species purely by measuring the distance between data and the centroids. Abstract data sorting relies on the exact mathematical logic as routing delivery drivers on physical maps. Once your k-means model is trained, its utility expands beyond just analyzing old data. You can now use it to instantly categorize brand new, unseen data points. When you feed it a new flower sample, the model simply checks which of the existing established centroids it lands closest to and assigns it to that group automatically. So, to bring it all together, k-means is a centroid-based, unsupervised learning algorithm used to find hidden groups inside unlabeled data. K dictates the number of clusters. Centroids are the mathematical center points, and inertia measures how tight and efficient those groups are. Now that you understand the mechanics, think about the unlabeled data in your own life. How could you apply this automated clustering logic to automatically sort your favorite movie genres or organize a massive, messy music library?